Hello everyone, this is Dr. Matt C. Howard and welcome to week 3 of Business 255. As you know, this week we're going to be covering t-tests, and actually this week we're going to be covering 2 different types of t-tests, so I'm excited for this. It should be a good, introduction. We've already did chi-square, but I guess a little bit more of an introduction into comparing groups, comparing group means particularly. So we're going to start with t-test, and then next week we're going to cover, or I guess next week is our test. But the week after we'll cover ANOVA. So this will be a good introduction to a lot of those concepts that will come back when we get to ANOVA after the first test. So what is a t-test? As I said, today we're covering t-tests. What is a t-test? Well, a t-test is a type of analysis that's used to determine whether group means are significantly different. So whenever you're doing a t-test, you're still looking at grouping variables. We're still looking at the same type of a lot of the same type of variables we were looking at for a chi-square test. So we're still looking at grouping variables like comparing classrooms. So our grouping variable would be classrooms, and we might have 2 classrooms, we might have 3 classrooms, we might have 4, but that grouping variable would be classrooms. We might have something like different factories. So we might have factory A, B, C, D, E, but the grouping variable there is what factory the participants are in. So we're still looking at grouping variables. We're still looking at the differences among the groups. The one difference between a t-test and a chi-square test, though, is, as you remember, a chi-square test was just looking at the number of people within those groups. For a t-test, you actually have another separate measured variable that you're comparing among those groups. So not only do you have the grouping variable, but you also have a separate measured variable. So for example, if we're looking at classrooms, we might have what classroom the participant is in for our grouping variable, but we might also give them a test, and therefore our other measured variable would be their test scores. So in that example, we would have classroom as our grouping variable, and we would have test scores as our measured outcome. Another example might be we're looking at basketball teams in the NBA, so our grouping variable would be basketball teams, what team you're on, and then we might measure the players' heights. So therefore our measured outcome variable would be height, and we could use a t-test. That example would be kind of bad for a t-test, but let's say we're just looking at 2 different NBA teams. We could use a t-test to determine whether there's a significant difference in the heights of those 2 teams. So long story short, a t-test determines whether group means are different based on a measured outcome. So you have your grouping variable and you have your measured outcome. One other thing important to know is, as I mentioned, we're covering 2 different types of t-tests. So the first one is a one-sample t-test. So when you're using a one-sample t-test, you only have one group. You have something like Dr. Howard's class. You have something like the students at South Alabama. You might have all the players in the NBA. So those examples are just one group. And you might want to determine whether the mean of that one group is significantly different than a specified value. So let's say we're looking at all the players in the NBA. We might do a one-sample t-test to determine whether their heights are significantly different than 6'6". Or we might use a one-sample t-test. If we had all the students in Dr. Howard's class, we could do a one-sample t-test to determine whether their homework 1 grade was significantly different than an 85. So therefore, in those examples, we have one group. We specify a variable such as 6'6", we specify a value such as 6'6". We specify a value such as an 80 on test 1. And we could perform a one-sample t-test to determine whether the group mean is significantly different than that value. Okay. Also, we could perform a 2-sample t-test. A 2-sample t-test tells us whether 2 group means are different from each other. So in this example, when we do a 2-sample t-test, we just have 2 groups. It's as simple as that. We have 2 groups. We might want to see whether their means significantly differ. So once again, in this example, some of the stuff I said before, we might have 2 classrooms, and we might want to perform a 2-sample t-test to see if their test 1 grades are significantly different. We might have 2 NBA teams. We might perform a 2-sample t-test to determine whether their heights are significantly different. So therefore, we perform a 2-sample t-test to determine if the means of 2 separate groups are significantly different on a measured outcome variable. So if you're confused about it, shoot me an email. I'd be happy to explain it more. So as you can see, we're going to go back to this chart that we've already seen once before. So we're still going to stay in the right side of this chart. So we're still looking at the difference between groups. But last time when we went to the question, how is your outcome gauged on this right side of the chart, before we said the numbers of members in the groups, and that was for a chi-square test. Now we're looking at a separate measured variable. So we're looking at the difference between groups. We have a separate measured variable as our outcome. And today we're going to cover the instances where we have one group, as well as the instances where we would have two groups we want to compare. So we're looking at the difference between groups. Our outcome is measured as a separate measured variable. And a one sample t-test we would use when we have one group in that instance. And a t-test or a two sample t-test is when we would have two groups. Okay, so we're going to start today by discussing the one sample t-test. So a one sample t-test analyzes the difference between a sample mean and a given value, and you provide that given value. So we would collect something like all the test scores from a classroom, and we would see, hey, is that significantly different from a value of 80? And we have to specify that value we're interested in. When you're doing a one sample t-test, it doesn't choose it for you automatically. There's no magic number everything should be compared to. Instead, you have to choose what value you want to compare. So conceptually, this is what a one sample t-test would look like. As you can see, we would have a distribution of scores for our sample. So that's what that bell curve is. We would have a distribution of scores for our sample. We would have mu, which is the mean. We would have that mean right in the middle of our sample. And then we would have to specify our value, which in this picture is represented as the C. So we would specify our value, and we would try to see if that value we specified is significantly different from the mean. So this is what it would look like theoretically. Okay, so when performing a one sample t-test, our null and alternative hypotheses are usually, the null is usually there is no difference between the mean and the selected value. So the null hypothesis is usually the mean and the selected value are not significantly different. And the alternative hypothesis, or our hypothesis, is there is indeed a difference between the mean and the selected value. That there is indeed some type of difference between the mean and selected value. So therefore we would perform a one sample t-test, we would get our p-value, and we would try to see if we can reject that null. We would try to see if we can reject that there's no difference, and then therefore assume that our hypothesis reflects the state of the matter. So once again, we would perform a one sample t-test. If our p is less than 0.05, we could reject that null. Once again, if p is less than 0.05, our results are statistically significant. So we can reject that null and say there is a significant difference if our p is less than 0.05. Okay. So once again, we just perform a t-test to determine whether we can reject the null hypothesis, and we use p-values to do this, just as I just now said. Okay. So once again, some questions that might be answered via one sample t-test. I've already said most of these. So is a class's average grade significantly different than a 70? We have a classroom, we measured their grades, and then we want to see if that measured outcome, their grades, is significantly different than a 70. Also, we could test whether the class's average height is significantly different than 5 foot 5 inches. And we could test, is a company's yearly revenue significantly different than $10 million? So we could collect a lot of data of a company. We could, so that would be our, I guess we would consider that our sample. We could see what their yearly revenue is over the course of years. And we could perform a one sample t-test to see if it's significantly different than $10 million. Okay. So some of y'all might be asking yourselves, when would we ever use this? And to be 100% honest, probably not all that often, or at least in my personal research as well as consulting experiences, I really don't come across it all that often. And the reason why is there's not that many instances ahead of time. I absolutely know without a doubt a certain value is extremely important. That doesn't happen in my research that often, and it doesn't happen in my consulting work all that often. It's very rare a company says, we have to make sure we're significantly different than this value. We have to make sure we're significantly different than this mark. Sometimes companies want to make sure they achieve a certain cutoff, but they can just look at the descriptive statistics to determine that. Typically, in my experiences, they don't go as far as doing a one sample t-test to answer that question. However, there might be some instances where a one sample t-test is important, such as when you know a predefined value is important. So like I said, if ahead of time you know a certain value is important, you might be doing a one sample t-test. Also, another example is when you have a certain expected value for a sample. So let's say that you're looking at a certain phenomenon in the workplace, and you already know, hey, I've looked at this phenomenon 4, 5, 6, 7 times. I've gotten somewhere around this same result every time. So you might want to look at it again in your new sample, and because you've already seen it several times, you could go ahead and expect that value. So you might would want to test whether the value you observed in the past holds for this sample too. And you could perform a one sample t-test to do that. Also, in some very rare instances, there's some common sense value. Sometimes just working in a certain industry, you know that certain numbers and certain values are important. So you might want to make sure that your sample that you collected is somewhat close to that important value. And then also in research, it could be important when you're performing a replication study. So a replication study in research is when you're trying to replicate, when you're trying to reproduce old results, what someone else found. So you could do a one sample t-test to see, are your results significantly different than what that other person found, than what that other person got. So those are some examples. So that's why we need to learn a one sample t-test. Is some of y'all in this class might come across instances in the future that you will need to do this. So there you go, we do need to learn it. Okay. One thing to note though is we almost always apply a one sample t-test on measured variables that have a clear established meaning. So usually things like height, weight, money. So height we can measure in inches, weight we can measure in pounds, money we can measure in dollar amounts. That has a firm meaning behind it. Each of those we can just say the number and everyone knows what that means. However, we typically do not apply a one sample t-test on things that do not have an established meaning. So we've talked before about Likert scales in this class. So things like when we give a survey that's a job satisfaction survey, and it says things on a scale from 1 to 5 indicate how happy you are. 1 not happy at all the way to 5 as happy as you could possibly be. That's a Likert scale. And typically we would not do a one sample t-test on that because those numbers don't have a clear established meaning. It's really hard to know, well, is a 3.5 really that much different than a 4 on a Likert scale? It's hard to tell if that's really a significant, meaningful difference there. So usually we just perform a one sample t-test on things with clear established meanings like height, weight, money, and so on. Okay, so I gave, in the email you should have received from me by now, if you're watching this video, I did give you a guide on how to perform a one sample t-test in Excel. So if you should follow that guide. You should make sure you go over that guide, follow all the steps to make sure you can do it yourself. But in this video, I'll go ahead and just cover the basic steps because there's one or two things that are a little bit confusing, and I don't want everyone having to email me saying, hey, I don't really get this. So instead, I'll just go over it quickly in this video. If you're comfortable with just using the guide yourself and not watching this part, feel free to fast forward. But I'm going to go over it quickly, just the general steps of the guide. I'm going to point out one or two things that might be confusing. Okay, so when performing a one sample t-test, oh, by the way, the link to the guide will be in the description of the YouTube video. So if you don't know where to find the guide, just look into the description of this YouTube video. So anyways, the data set in the guide is going to have test grades. As you can see, we have 30 different test grades for a class. So this class has 30 students. And in this example, we want to see whether the average of these test grades are significantly different than an 80, whether it's significantly different than the value of 80. So as I mentioned in the guide, Excel doesn't have a built-in method to do a one sample t-test. I know that sounds crazy, it can do so many other things. Why can it not do such a basic analysis? I have no idea. I have no idea why they didn't program that. But anyways, we still have to figure out how to do it in Excel. And in Excel, you can kind of trick it into doing a one sample t-test. You can do it in a kind of fake way. So to do it in a fake way, to do a one sample t-test by tricking Excel, first we need to enter the number we're interested in. So if you're following along, you would just enter a label for that second column. I like the label number, and you would type in the number you're interested in twice. You would type it in the second and the third row. So in this example, we're interested in the number 80. So we would type in that number 80 twice in the second and third row of column B. So go ahead and do that. Then, like our other analyses, or what we're going to cover later in this semester, you're going to go to the Data tab, and you're going to click on the Data Analysis button. If you haven't activated data analysis in Excel already, I also have a guide for that, so check out mattchoward.com, and I'll show you how to activate that tab in Excel. So anyways, if you do have it, click on Data Analysis. That should open up this window, and this is where it gets confusing. This is where I wanted to make sure everyone's on the same page. In this window, we're actually going to click on t-test to sample assuming unequal variances. So this is going to sound weird, this is going to sound crazy. Typically, we don't click on analyses that aren't exactly what we want. Usually, data analysis, this plugin or this add-on in Excel will have the analysis we want to do, but this time it doesn't. So we have to tell it we want to do a t-test to sample assuming unequal variances. And then we're going to push OK. I know that sounds weird, it's just what we got to do. Okay, now you're going to click on this first button, that variable 1 range button. That we're going to tell Excel what we want our first group data to be. We have to show Excel where our data is for our first group. So we're going to click on that button, and we're going to tell Excel our first group is that test grade column. So we're going to click on the first cell, and we're going to drag our mouse all the way down until everything in that column is highlighted, until we've highlighted all of that data. So go ahead, highlight that data, and then push that other button that's highlighted. Push that other button I have highlighted for you. And there we go. In the variable 1 range section of that window, you should have your test grade data already put in there. It should be in there now. So let's go ahead and click on that button for variable 2 range. So this is also where it gets a little bit confusing. So what we're telling Excel is we're saying we have this other group, when in reality it's just the number we want to compare it to. So we kind of have to lie to Excel because we just want to compare our results to a certain number. We type that number in. So we kind of have to lie to Excel and tell it, well, that's a different group. And I know it's not a different group. I know that's just the number we typed in, but Excel is stupid, so we can get away with it. Okay, so go ahead, highlight those 2 numbers you typed in, and then push the button that's highlighted. So that will trick Excel into thinking that's a separate group, and we can compare the group 1 data to those numbers we typed in, to the number 80. And then once you do that, push OK. So this window is going to give us some information. So the first part we want to look at is the mean. So in the variable 1 column, that's the main column we want to look at when doing a 1 sample t-test in Excel. So in that variable 1 column, it's going to tell us the mean of our group. It's going to tell us the mean of our group when we're doing a 1 sample t-test. And as you can see, the mean is a 90.9. So the mean of this is a 90.9. So we can already tell immediately off the bat, that's pretty different from an 80. That's pretty, that's a little bit higher. Do we know if it's significant yet? Not yet, but we do recognize that is pretty high. Excel will also give us our test statistic, our t statistic. So our t statistic in this is a 7.64 if you're rounding to 2 significant figures. So we have a 7.64 would be our test statistic. Do we know if that's significant? We don't know yet. That is a test statistic. We would want to report that. We would want to tell people this is what our test statistic is if we were doing this for consulting work or if we were doing this in the workplace. But we don't know if that's significant yet. So fortunately, Excel does give us the p-value directly. Fortunately, Excel does directly give us the p-value. And I'll explain a little bit more about this when we cover 2 sample t-tests in a few moments. But I just wanted to directly tell you the answer for this one, and then we'll talk about it more when we're doing the 2 sample t-test part. So this does give us the p-value directly. As you can see, the p-value for this is 2.01 e negative 08. So what in the world does that mean? How can you have a number that has an e in it? So Excel, when a number is extremely small or extremely large, will present it in scientific notation. So this is scientific notation, and what it's actually saying is 2.01 times e to the negative 08. So one way to think about this, or the correct way to think about this, is if it's e to the negative something, that's how many times you should move your decimal point to the left. That's how many times you should make your decimal point go to the left, or you should make your number that much smaller. So when it's e to the negative 08, you should move your decimal point to the left 8 times. So therefore your number turns into decimal point 0.000000201. So once again, it would be decimal point 0, 0, 0, 0, 0, 0, 0, 2, 0, 1. So that would be a decimal point followed by 7 zeros and then 2, 0, 1, because we had to move that decimal point over to the left 8 times because it was e to the negative 8. So therefore our p-value is extremely small. That's extremely tiny. That's so small it's hard to even imagine something that small. But the main thing to recognize is it's less than 0.05. So the main thing to recognize is our p-value is less than 0.05 because it's so incredibly small. So what happens when our p-value is less than 0.05? Do you remember? Can you guess? That's right, we reject the null hypothesis and our results are statistically significant. If your p is less than 0.05, we reject that null hypothesis and our results are statistically significant if our p is less than 0.05. So in this case, our p was indeed less than 0.05, so therefore our group mean is significantly different than an 80. So we know our group mean is different than an 80. So there we go. We know that our our class test average, our class grade average, was significantly different than an 80. And we can go back and look at that mean at the very top to determine whether it's significantly more or significantly less. So when we look at this, our mean was a 90.9. We know that that was significantly different than an 80. So we can see our class average was significantly greater than an 80. We know it was significantly more than an 80. Because that mean is greater than 80, that mean was statistically significantly different, so therefore it was significantly more than a value of 80. So we would reject the null hypothesis, we would say our results were statistically significant, and we would say our results were significantly greater than a value of 80. So there we go. We figured out how to do a one sample t-test. If it's a little bit confusing to you still, go through that guide that I provided you. It should be in the description of this video. And then ask me any questions if you still need help. I'm always here to help. I'm always here to answer questions. Okay, so let's move on to the two sample t-test. We already did a one sample t-test. Now let's do a two sample t-test. So what is a two sample t-test? Well, the textbook definition says it's used to determine whether two sets of data are significantly different from each other. I don't really like that definition a lot. It's a little bit too textbooky to me. So instead, I like this one better. It's used to test whether the means of a measured variable in two groups is significantly different. So it's used to test whether the mean of a measured variable in two groups is significantly different. So in this example, we have a grouping variable. That grouping variable has to have two groups and only two groups to do a two sample t-test. And we have to have a measured outcome variable. So we have to have two groups and something that we've measured in those two groups. And when we're doing a two sample t-test, we're comparing the mean of the two groups on that measured variable. So once again, going back to this chart, we're looking at the difference between groups. Our outcome is gauged. This is a little bit different than I wanted it to be, but we'll keep with it. So instead of it being the number of people in the groups, which I have listed here as categorical by accident, instead of being the number of people in the groups, or something measured categorically, we have a continuous outcome. We have it measured as a separate outcome variable. We have something measured that's a separate outcome variable, and it's going to be continuous. And then how many groups do you have? We have two groups. So therefore, since we have two groups, we have a separate measured outcome variable, and we're looking at the difference between groups. We're going to do a t-test. We're going to do a two sample t-test. So what are some questions we can answer with a two sample t-test? So we could have a classroom, we could give a test, so the test would be our measured outcome variable. So the test would be our measured outcome variable, and we could measure whether people on that test, if they were males or if they were females, if they were men or were they women. We could do a two sample t-test to determine, do women have better test grades than men on this test? So therefore, grouping variable would be gender, and then our separate measured outcome would be test grades. Similarly, we could also have a classroom and we could have men and women. We could measure male versus female, and then we can measure their height. So therefore our grouping variable would be gender, and then our measured outcome variable would be their height. Another one would be, do people in a class taught by Dr. Howard perform better on a test than those in Dr. Smith's class? So our grouping variable would be classroom. We would have two groups, Dr. Howard versus Dr. Smith. So we have classroom with two groups, Dr. Howard and Dr. Smith. And the measured outcome variable would be test scores. So we'd give a test, and we would grade the test for each of the participants, and therefore our measured outcome variable would be test scores. And then the very last example I'll give is, do employees in training group A have better performance than those in training group B? So our grouping variable is what training group or what training program you went through. You could have training program A, you could have training program B, and then you can measure their performance. So our measured outcome variable is the employee performance. So we're doing a t-test to compare the performance of the two groups between training group A and training group B. So there you go, those are different examples. So when performing a t-test, that's a typo there, it should not be t-test test, but when performing a two-sample t-test, our null and alternative hypotheses are usually, the null is that there's no difference between the mean of the groups, and our hypothesis is there is a difference in the mean of the groups. So we perform a two-sample t-test, we get our p-value. If our p is less than 0.05, we can reject our null, we can say our results are statistically significant, and we say that there is a difference in the mean of those two groups. So therefore, we can say that there is a there is a difference in the mean of the two groups if our results are statistically significant. If our p is less than 0.05, we can say there is a difference in the mean of the two groups. Okay, so this is visually what a two-sample t-test might look like. As you can see, we have group A, we have group B, and they have their own distributions. So this might be test scores. So as you can see, group A had a much lower mean than group B. So A is all the way over there on the left, B is all the way over there on the right, and we can perform a two-sample t-test to see if this difference is statistically significant. If their means that are that brown line are far enough apart to say that is a statistically significant difference. So if we had something like that with data, with numbers, and we performed a two-sample t-test, that would probably be statistically significant. That looks like it's a pretty big difference. Those distributions hardly overlap at all. But here's another visual representation. Let's say we had two groups, a blue group and a red group. We measured them on some measured outcome variable, and then we performed a two-sample t-test. It's much less clear, it's much more unclear if this would be statistically significant. There is a difference there, but there's a lot of overlap in those distributions. That's not that far apart. So it's much less certain whether this result would be statistically significant. So there you go. So when would we use this? Honestly, we use this quite often. I use it very frequently in research, and I've used it very frequently in my consulting work. Typically, we would use this when looking at things like differences between training groups. So all the time companies are making new training programs, all the time companies are redoing their old training programs, and typically how they test the effectiveness of their new training program is they'll have one group that does the old training program, the other group does the new training program, and you measure their performance afterwards, and you perform a t-test to see if there is a significant difference. And if there is a difference, you tend to go with the better one. If there's not a difference, if you can say they're roughly the same, you then go with the cheaper one, because they're pretty much the same. Another example you would do a two-sample t-test is work units. Let's say you have two work units and you want to see which one performs better, or if there is one that's significantly better than the other. You would then collect data regarding those two work units, and you can perform a two-sample t-test comparing the two. Also, companies all the time do two-sample t-tests when comparing geographic regions. So if a company is thinking about opening a new location, and they're deciding whether they want to do it in geographic region A, geographic region B, if they want to do it on East Coast versus West Coast, then they would usually collect data regarding those two locations, and they could perform a two-sample t-test to compare those two locations to determine which of those locations is better and if there is a significant difference between the two. And in general, any time that you would make a bar chart with two bars, you would probably then want to do a two-sample t-test. You would probably then want to do a two-sample t-test. So therefore, anytime you would think, oh, I need to visualize this data by making a bar chart with two bars, then you would go ahead and do a two-sample t-test. Okay. So we can perform a t-test to determine whether we can reject the null. So we still use p-values to do this. If our p is less than 0.05, we would still perform a t-test to determine whether we can reject that null hypothesis by using the resultant p-values. Okay, so how do we perform a t-test? Fortunately, we're going to use Excel, and fortunately for once, Excel is actually going to have a very direct method to perform a two-sample t-test. It's built into that data analysis plugin. Okay, so once again, here's data. This is also, it should be, I believe, the same data that is on the guide that I provide. So it's the guide that I sent you for this class, or it's the guide that's in the description if you don't have access to it. So go ahead and click on that guide if you want to follow along with this video and download that data. So in this guide, we have two classrooms. We have Dr. Howard and Dr. Smith, and then we have their test grades. So in this example, we're wanting to compare the test scores of Dr. Howard's class versus the test scores of Dr. Smith's class. We're wanting to see, do people in Dr. Howard's class on average perform better? Is there a significant difference in the mean of those two groups? Or are they roughly the same? Is there no real difference between the mean of those two groups? So to do this, we're going to start by once again going to Data and then clicking on Data Analysis. So we're going to go to the Data tab and click on the Data Analysis button. Once again, if that's not there, go and look at my guide on installing or activating the Data Analysis add-on in Excel and activate it, and then it should be there. But go ahead and click on that button. And like we did for the one sample t-test, we're actually going to click on the same exact analysis for the two sample t-test. We're going to click on t-test two sample assuming unequal variances. And as you'll see, there's that one above it that's assuming equal variances. Just go ahead and ignore that one. We're not going to talk about the difference between assuming equal versus unequal variances in this course. But typically, if you're assuming unequal variances, it tends to work out better across most situations. Typically, there's not a situation that really makes that big of a difference if you assume unequal variances. So I feel safer using that one. I feel better just assuming unequal variances because the results, I don't know, they tend to be safer in my opinion. So go ahead and click on that and then click OK. And just like before, we have to tell Excel where our group 1 data is and where our group 2 data is. We have to tell Excel where we're putting Dr. Howard's data and where we put Dr. Smith's data. So click on that first button to show it where the first group's data is. So we're just going to highlight the data for Dr. Howard's class. We're just going to click on that first one right there and drag it all the way till Dr. Howard ends. And we're only going to highlight the data. We're only going to highlight the data there. We're not going to include any labels in this example. So once you highlight this data, push that button over there. And now Excel knows where that group 1 data is. That group 1 data should now appear in that little window. Now we're going to do that for the group 2 data. So we're going to click on that button. We're going to click on the button to highlight the group 2 data. And then we're going to go ahead and highlight that group 2 data. We're going to go ahead and highlight that group 2 data. So we're going to highlight it. As you see, do not include labels again. We're just going to highlight the data. We're then going to click that button. And now Excel knows where our group data is. Now Excel knows where our group data is. And we should remember that we put in the variable 1 range. For variable 1, we put in Dr. Howard's data. And then for variable 2, we put in Dr. Smith's data. We should remember which one went where. Okay, so now push OK. And it should give us results. So as you can see at the very top there, the variable 1, which was Dr. Howard, the mean for that was 88.5. And variable 2, which was Dr. Smith, the mean for that is 75.3. So already, once again, we can see that's a pretty big difference. That's pretty notable, at least in my opinion it is. Do we know if it's statistically significant yet? We do not know that yet. We just know that the mean for Dr. Howard was 88.5, and the mean for Dr. Smith was 75.3. Okay, so now we look at the test statistic. And we see that the test statistic for that is 2.78 if we're rounding to two significant figures. So we see that the test statistic is 2.78. So that's important to report. That's important to know. That's important to tell whenever you're doing consulting work. The t statistic for our two sample t-test was 2.78 in this example. But do we know if it's statistically significant just based on that? We can't quite tell yet. We don't quite know yet. So therefore we have to look at the p-values. So this is the part before that I told you that I would mention once we got to the 2-sample t-test. I didn't mention this before we did the 1-sample t-test because I didn't want to confuse everyone when they looked at it for the first time. But when you're doing a 2-sample t-test in Excel, or a 1-sample t-test for that matter, it will actually give you results based on if you want it to provide a 1-tailed or a 2-tailed p-value. It gives you the results both for a 1-tailed and a 2-tailed p-value. You should have learned the difference between these two in your first stats course. You should have learned the difference when you took stats previously, because this should be stats part 2 for everybody. However, just in this class, I'm just going to keep it simple for you. I'm just going to keep it easy. We're always going to want to look at the 2-sample p-value in this course. We're always going to want to look at the 2-tailed p-value in this course. Sorry, I said 2-sample before. We're always going to want to look at the 2-tailed p-value in this course. I prefer that because it tends to be more conservative. It tends to be that you actually have to have a pretty significant difference for that to be significant. And I like that. I like to be a little bit harsher on my statistics. I like to be more conservative on my statistics. I don't want things just to be significant just because I've made a random statistical decision. I want to make sure they're significant because they indeed have a difference, because they're indeed significant. So therefore, we're going to always use the 2-tailed p-value in this class. So let's go ahead and look at those 2-tailed results. This is another thing I did not mention before, but the output will indeed provide a 2-tailed critical value. So this is the value your t-statistic has to be above for your p-value to be less than 0.05. So once again, this is the value your t-statistic has to be above for your p-value to be less than 0.05 and for your results to be significant. So this is almost identical to what we were doing before with the chi-square test and finding that cutoff value in the table and then comparing our test statistic to the cutoff value. Almost the exact same thing, except Excel automatically provides you the correct critical value, and then if you want to, you could compare your t-statistic to that critical value to determine if your p is less than 0.05. Fortunately, Excel also will provide your p-value. That's a wonderful thing. That's an amazing thing. Excel will also provide your p-value. So therefore, you don't even have to do that comparison yourself. You don't even have to look at that critical value. And if I remember correctly on the homework, I don't even ask you to provide it. I don't even ask you to look at that critical value. I get you to provide the means, I get you to provide the t-statistic or the test statistic, and I get you to make inferences based on the p-value. And I don't even get you to report that critical value. So let's go ahead and look at the results here. Let's go ahead and look at what the results tell us. So the results tell us that our p is 0.015. Our p is 0.015. So based on that, can you say that our results are statistically significant? And obviously you can. So were our results statistically significant? Hopefully you got that right. Yes, our results are statistically significant. Our p is less than 0.05. Our p is less than 0.05. So we can reject that null hypothesis, and we can say our results are statistically significant. We can therefore assume there is a significant difference between the means of these two groups. Because we reject the null, we go with the alternative hypothesis, and therefore we can say there is a significant difference in the means of these two groups. So our results are statistically significant. So the very last thing we should look at is, now that we know there is a significant difference, how do we know which one was bigger, and how do we know which one was significantly larger or significantly smaller than the other? Of course, we can go back and look at the means like we did before. So we look at the means, and we saw before, and we said this before, the mean of Dr. Howard's class was 88.5. The mean of Dr. Smith's class was 75.3. So based on that, we know that Dr. Howard's was larger. So therefore, because we can say the mean of Dr. Howard's class was larger than Dr. Smith, because we can say there's a significant difference in those means, we can thereby say that the mean of Dr. Howard's class was significantly larger than Dr. Smith's class. We can therefore say there's a significant difference in the means, and thereby the mean of Dr. Howard's class was significantly larger than Dr. Smith's class, because that mean was larger and it was significantly different. Okay, so the results of this, there was a significant difference, and the mean of Dr. Howard was significantly larger than Dr. Smith, with a value for Dr. Howard of 88.5 and a mean test score of Dr. Smith of 75.3. And that's all I just now said right there. Test statistic, that's what we found. The critical value, that's what the critical value was. I don't ask you to report it, but I have it there just for you to know. The p-value was indeed less than 0.05, so we can say our results were statistically significant. So therefore, from this, we can reject the null hypothesis. We don't have to use any tables. We don't have to use that chi-square table from before, because Excel does it for us. That's one of the benefits of having computers, when they can actually do the analysis. Okay, and that's exactly what I said before. We can say there's a significant difference, so therefore we have to look at the means to determine whether that difference is actually significant, or which one was higher than the other, and we see that Dr. Howard's was higher. Okay. And I had this one slide. Actually, this slide has a quick typo on it. So that's all we need to know about t-tests. So as long as you know all that information I just covered about t-tests, you should be good for the test. You should be good for the homework. But make sure you do the guide. Make sure you learn how to do this in Excel and do it on your own in Excel. I have a feeling that some people, they just try to use the guide when they're doing the homework for the first time. Don't do that. That's not the right approach. What you should do is you should watch the video. You should then do the guide using the example data set. Then you should do the homework. And you can use the guide, you can use the video to help you with the homework, but you should not be doing the guide for the first time with the homework. I think that's where some people are getting pretty bad scores on their homework, because they're trying to follow the guide, and the first time they do the guide, they use it with the homework data set and they just go ahead and submit whatever they get. No, don't do that. Use the guide using the example data set the first time, and then do the homework, because I think a lot of people don't even notice when they're messing up on the guide, and they just go ahead and submit the homework and hope for the best. No, don't do that. Okay, so with this class, as you know, next week we have a test. So the next lecture we're going to have, so that should say next lecture, we're going to start with ANOVA. We're going to cover ANOVA in this class. And just FYI, an ANOVA is like a t-test with more than 2 groups. So if you understand a t-test, you're going to have a good start on what we're going to cover after the first test. You're going to be good after that first test. So that's all for this week. Thank you for listening. Thank you for watching. If you have any questions, shoot me an email. Always available to chat. Always available to talk about statistics. But until then, I'll talk to you in 2 weeks because we have a test next week.